So in the last video, we figured out a basic model for a solar cell, and we said that that was just some current source, which depends on the incident solar radiation, so that's our photocurrent, and some diode. And this diode is just the PIN structure. So this is the PIN structure of a traditional solar cell. And now we're curious what happens when we attach a load resistance to this. So some load resistance. So we want to extract some energy. We want to get some energy out of this system. And we do that generally by modeling the thing that we attach this solar cell to as a resistor. And let's say that we're interested in the current flowing through this resistor IL. We could also be interested in the voltage, but the current is generally going to be more useful for us. So let's just try different values of RL. So first let's try RL equals 0. So what happens when this is just a short circuit? Well, we know the voltage across this short circuit has to be equal to 0 because it's just a wire, which means that we're not applying any voltage to this diode, and all of our photocurrent is getting shunted through this branch. So this is our photocurrent. And this is also known as the short circuit current. So I short circuit, SC. Photocurrent is more typically used for photodiodes, and short circuit current is more typically used for solar cells. Because in general, we don't have access to what this photocurrent is. Like we can sort of apply different amounts of light to the solar cell by, putting it under some shade, for example, as we're irradiating it. But in general, this short circuit current is a characteristic of the solar cell that we can measure. That's when it's out in the sun. Okay, so when this RL is just 0 ohms, so when it's a short circuit, we have IL is just equal to our short circuit current, which is just the current generated from our photons. But unfortunately, the power that we're getting out of this, which is just the voltage across our load times the current, is 0 because we've got no voltage across our load. So this isn't a terribly practical configuration. So let's try a different value of RL. Let's try a value slightly over 0, but not too much more. And let's also say that the open circuit voltage of this cell is known. Let's say that it's 0.6 volts. And let's also say that we measured the short circuit current and we found it to be an amp. And let's say initially that we've got RL is equal to 100 milliohms. So 100 milliohms. Then what is this IL? So what is IL based on what we know? Well, if all of this current were to flow through the resistor, so if IL was just equal to our short circuit current, then it would be equal to an amp. 1 amp, well, I don't know what I did there. It would just be equal to an amp. And the voltage across this load would just be the short circuit current times the load resistance, or about 0.1 volts. And so this voltage here is going to be about 0.1 volts, which means our diode here is slightly forward biased, but the current that's flowing through it, so the current I diode that's flowing through it, is going to be tiny. It's going to be negligible. So long as the voltage is much less than the open circuit voltage, there's going to be essentially no current flowing through this diode. But as we start to increase the value of this resistor, so let's say we were to increase it to 500 milliohms, for example, so 500 milliohms, then we'd start to get an appreciable voltage across this diode, so some appreciable voltage VL, and this current would predominantly start flowing through this diode. And then as RL approaches infinity, so maybe let's say RL is several mega ohms, for example, then almost all of this current is flowing through this diode, and the voltage across here will just be the open circuit voltage, because it's as if this resistor doesn't exist anymore. So the IV characteristics for a solar cell sort of look like just an upside down diode. So as we initially, so if this is our voltage, so our load voltage, and this is our load current, so initially our current, our load current, is just approximately equal to the short circuit current because all of our current is flowing through our resistor. So all of the current is flowing through our resistor. And this diode current is so tiny that we don't even notice it on our plot. But eventually, once we get kind of near the open circuit voltage, so once we get close to the open circuit voltage, the current starts to decrease. So the load current starts to decrease. And as we approach the open circuit voltage, our load current will become zero. So our load current will be zero. And you can generate this curve by actually solving the equations for this this solar cell circuit. And we can just do that real quickly right now. So let's just apply, let me erase this stuff so we have a more clean circuit to work from. So we've got a few things in parallel. So we just want to use KCL at this node, for example. So we know that our short circuit current, ISC, is just equal to, so this is ISC, this is equal to our diode current plus our load current. So our short circuit current is equal to our diode current plus our load current. But the load current we can just write as the load voltage divided by the resistance, and the diode current we can just write as a diode. So I sat e to the VL over the thermal voltage minus 1. And so we have our final equation. The short circuit current is just equal to this diode current, which is in terms of the voltage, plus the load voltage. Now, unfortunately, this is a transcendental equation. So this is a transcendental equation, and it's unsolvable analytically. So we can't get IL as a function of VL, for example, just or as a function of the load resistance. We have to actually solve this numerically. So if you plug in different values of RL, you can solve this equation numerically for VL, and then you can figure out the load current by just saying that it's just VL over our resistance value RL. And if you plot enough values of RL, you'll start to regenerate, or you'll start to generate this curve. Now, one last thing, how do we maximize the power? So how do we maximize the power to our load? Well, we want to maximize both the current and the voltage, or we want to maximize their product. And so we want to get as close as we can. So we want to get as much current as we can without decreasing the voltage across our load. And so we want to be operating somewhere about here, or maybe here, just as the voltage starts to just as the current starts to decrease and our voltage continues to increase. So this point, so this operating point will give us the maximum power. And you can actually plot the power as a function of, for example, the load current or the load voltage, and you'll get some local maximum. So you'll get some value for which some load current value, let's call that IL max, for example, where your power is maximized. And that's just an exercise in numerical analysis at that point. It's just plotting stuff. But the intuitive picture of this is really the most important. So when our resistor is very small, when RL is approximately 0, then our load current is very close to the short circuit current. And as we slowly start to increase RL, we're increasing the voltage drop across it until eventually we increase the voltage drop so much that the current starts to flow. So at this point, current starts to flow through the diode. So current through diode. And as we continue to increase RL to infinity, so at this point we have RL is equal to infinity, then the voltage gets larger and larger, but the current starts to drop off a cliff. And so at this point, all of our current is flowing through the diode. Flows through the diode. And so in our circuit model, we've got our short circuit current our diode, and our load resistor, RL. And so when RL's infinity, almost all of the current is flowing through the diode. When RL is close to 0, almost all the current is flowing through it. And if you want some points in between, you can just use KCL to figure out an equation for it. And you can physically plug in different values of RL and then solve for VL and IL. So I hope you enjoyed the video. If you did, please give it a thumbs up below and subscribe to my channel. If you have any questions or comments, please post them down below and I'll try to get back to you as soon as I can. Thanks for watching. See you next time.